or minus J over omega C. That's just common sense, right? The normalized value of the capacitive reactance, or impedance, would be simply, and I guess you'd put it as small x sub c, is simply 1 over J omega C times Z naught. Now that's the normalized, quote, impedance, or the normalized value of x sub c. Y'all follow me? Now the normalized value of y, the admittance associated, or the admittance element, would be 1 over x of c, and I don't care what you want to call this, y of c maybe, is J omega c times Z naught. Y'all follow me? That's positive J, right? So keep this in mind. Anytime it's positive J admittance, it's a capacitor, always. If it's minus J admittance, it's an inductor. Y'all with me on this? Now this is normalized, right? So what we can do is equate this to the value we need, which is 0.22, right? So I go ahead and I say, I'll do it right here, J omega here times C Z naught is equal to J 0.22. Nothing fancy, just equating it, right? Now we want to find the value of C. Always the element values are the critical ones. So to get the value of C, I can remove the J, and I take 0.22, this is going to be small, over Z naught, that's 50, times 2 pi times 10 to the 9th, right? I don't know what that is, but it looks like it's in the range of maybe hundreds of picofarad. Can you tell me what that is?
It's 70 times 10 to the negative 12.
750?
70.
70 times 10 to the minus 12. 70 picofarad. You're approaching what I would be comfortable with engineering. When you're getting down to something like below 50 picofarad, lead length will have picofarads in it, all right? It gets down to the point where you almost have, if you need that value, you almost want to put something in there you can adjust a little so you can modify it once it's in the circuit. I'm just trying to level with you. This is just some insight from me personally, because I've learned this lesson in some respects the hard way when I had to do projects, and I realized there's no, I mean, just breathing on it changes it a couple of picofarads. So what I try to do is put either, you know, they have adjustable like capacitors where they have like plates woven into each other, and you move it and they open the plate, they change the actual amount of capacity. That's really nice on something like this. But if you ever do this, I'm going to level with you. Don't use a regular screwdriver to do this. Don't use one of these jeweler screwdrivers. It's got to be something that's made of like a plastic something with no ferrous material, or else you'll never get it on right. All right, and you adjust it that way. That way, the actual element you're using, or the tool you're using to adjust it, won't change the actual resonant frequency. I'm just leveling with you. I've had to do this. Anybody else use these tools? Use any kind of like ceramic or plastic tools, because metal tools would change the electrical oscillation frequencies and stuff. You have?
They told us in lab, guitar picks are a good idea.
Yeah, they will work, but a lot of times you're going down through like a bunch of wires, and they have dielectric screwdrivers. Have you all seen these or not? You have? All right. Some are ceramic. I'm going to just caution you about using ceramics. I haven't spent a fortune on this, but ceramics are expensive and they're brittle. So if you bend one a little and it snaps, you might be out $40. Plastic, you can bend a little. It's forgiving. All right. Anyway, those are the values. Can you confirm if that's the right answers, anyone? Yeah? Y'all follow me the technique. Let's do one now. We're going to be inside the rotated circuit of impedance. We're going to talk about how to deal with that one, all right? So I'm gonna erase all this. Any questions before I do? Yeah.
How do we calculate the input impedance to, like it says confirm your design by calculating the input impedance?
After we put this on? After we do the, or not?
Yeah, I guess at the end.
All right, at the end, what's it gonna be anyway? What's the impedance right here? Input impedance, right? Anyway. What was the whole goal of what we were doing? We were matching it, right? All right, what's the reflection coefficient right here? It's right at the center. It's 1. What does that mean? The input impedance is Z0. Y'all follow me? The whole idea of what we're doing is, we want this thing to look as though it is just Z0. That's the goal of all this stuff. So it's matched. That means all the power goes down and is absorbed by the load. None is reflected. Y'all follow me? That's the goal of this whole thing. No reflections. And if there's one lesson I've learned the hard way, is that if you get reflections, especially on an expensive antenna design, it is so bad, it's worse than you did nothing at all. All right, because then they spend money and fabricated it, and now you're looking real bad. That's a personal lesson I learned this. Anyway, y'all with me on that, guys? I want to do the first one now with me. I think you can do it. What time is kickoff this weekend, Jacob?
6.
A night game is going on? Okay. 6 our time or Eastern?
Our time.
All right. Is it going to be cold? Up there?
I don't think it's gonna be too bad. I think it's gonna be like 60.
Oh, that guy. I saw some games. I don't know. I think they were up in Michigan, but I'm not sure. Snow was falling. I mean, it was on some sports. They had some like sports broadcast on when I was viewing it, and I've never played in snow. I mean, I played sandlot football in snow when I was young, but I never played like real. You know, the problem is you can't see the lines. I mean, you can't see anything.
Never thought about that.
That's back in the day, though. Who knows what they got now? Anyway, here we go.
Heated lines to melt the snow.
That'd be kind of cool.
Appreciate green.
That works out in your favor, right? 'Cause you just scoot a little snow this way, scoot a little snow that way. Yeah, we're good.
Yeah, it's all right.
All right, I think it's 10:11. Was that the first one, guys?
10:13.
10:13? Sorry. Go ahead and give me the problem.
Load impedance of 10 plus J15.
All right, guys, you're gonna have to pay attention to this one, because this one, you have to have good eyesight to appreciate. Go ahead, xenon 50.
15.
All right, you want an L section matching network, right?
Yeah.
All right. This is part 2. This is where, when I take the value of the magnitude of ZL over Z0 here, it's less than 1. All right? It's not only less than 1, it's inside rotated circle. So, first step, as always, find ZL, which is capital ZL over Z0, and that's going to be 10 plus J15 over 50. First, agree with me that that's correct. Y'all agree with that that's the normalized impedance? Y'all see it? All right, now here I'm going to plot it. And that's going to be 0.2 plus J.3. It's somewhere like right about here. And that would be ZL here in 0.1. And that's 0.2 plus J 0.3. Let me draw it up. This purple represents the 0.2 trajectory, the real part. Y'all follow me? I want to just plot that out. Now here's what I'm thinking in the back of my head. If I add a value of J plus or minus something to this is impedance, so it'd be added in series. Does everybody follow me on this? It would be added in series here because it's a normalized impedance I came in on. I can get to the rim, right? And that's my goal. The minute I get here, I know if that's the impedance, this would be the admittance. Y'all follow me? The minute I get on the rim, if that's the impedance, if I go to the other domain, 1 over that, I would automatically be on the R=1 circle, which is where I want to be. And then I could add admittance and get right to the center. Y'all follow me on that? So that's my thoughts. That's how you do this. So with this, by the way, I should say this. We could go this way. Y'all follow me? We could add a minus J something. That would be a capacitor. Y'all follow me on that? But I'm going to add an inductor, and generally speaking, here's the one thing you remember. Almost always, if you're going to do this right, you'll add inductors in series. Here's why. If these are being used with BJT circuits, do y'all remember how you have to use DC biasing at first to turn on the BJT, the bipolar junction transistor? And you want DC to get through it. Well, DC don't get through a cap. Y'all follow me? So that's the reason if you put an inductor in there, you can have a self-biasing network and you don't have to worry. That inductor looks like a short circuit to DC. All right, that's real important to remember. So we're going to add an inductor. We're going to go this way. So this is, could you go ahead and look on this trajectory, the 0.2, and tell me where it intersects the 1 circle right there.
0.4.
All right, so it's 0.2 plus J 0.4. That's 0.1, this would be 0.2. Y'all agree with that? Everybody see it? Okay, Jim? All right, now, how much did I add? Well, I started at 0.3 and I ended at 0.4. I added 0.1. Y'all see that, class? So that means right here, in series now, I'm going to have J 0.1. Right? That's an impedance. That's 0.2. Now, I'm going to go where? I'm going to go right through the center. You were asking about this. This, whatever impedance is right here, that's call it Z prime. This is Y prime, and it's just 1 over that Z prime. Whatever the value of the normalized impedance is on the rim, 1 over that better have the real value of 1. Now, can somebody just do this for me? Take 1 over 0.2 plus J.4.
1 minus J2.
So this right here is going to be 1 minus J2. Go ahead and confirm that, class.
He's right.
Y'all know how I got it, right? All right. Once I'm there, this is 0.3. Now I'm doing 1. Remember, that's admittance, right? Now I'm going to add an admittance that has a positive value, right? That's minus J2, right? Or 0.2. Is it 2?
It's 2.
2.
2. So I'm going to add a positive J2, right? To get me to here. What's it? 1, 2, 3. This would be 0.4. It would be dead center, and that's where we want to go, right? That's our goal, to get there, get rid of the imaginary part. So that means I'm adding an admittance here of J2. Admittance, right? And the way you tell is, Normalized impedances are always in series, normalized admittances are always in parallel, shunt. Okay, class? With me? All right, let's go about calculating these values. Start here. That's a series element. It's got a positive J. What is it in terms of it? Is it a capacitor or is it an inductor? Y'all know it's an inductor, right? Positive J inductor. So start with the impedance of an inductor, J omega L, right? I like doing it this way. Some people don't like the redundancy, but it helps burning it in your memory so you don't forget. Now I have to normalize that, right? So I go ahead and I divide by Z naught. Now I have the normalized value of an inductor's impedance, and that value has to be 0.1, or J.1, right? Y'all with me? Y'all see
Yeah.
it, guys? So that's equal to J 0.1. You can forget the J's. L here is going to be 0.1, right? Times Z naught over omega, or 0.1 times 50 over 2 pi. What's the frequency for this one?
1 gigahertz.
Is it still 1 gig? Times 10 to the 9. Can you give me what that value is? This looks small too. It's nanofarads, I think.
Yeah, 7.95 times 10 to the negative 10.
7.95 times what?
10 to the negative 10.
That's 0.795 nan. All right. Times 10 to the minus 10. That's getting down there. That's 0.795 nanometers. That's not much. Y'all with me? Okay. We got that. Next we need this. That's a normal, I mean, that obviously is positive J, it's an admittance, right? And again, I'll do it the way I tell people to do it so they don't mess up. I'll do it right here. A capacitor has an impedance of 1 over J omega C. I'm just going through what I did last time. Now when I normalize that impedance, I get this, right? That's the normalized impedance of a capacitor, right, or reactance of a capacitor. Now I want the normalized admittance associated, so I take 1 over that. And I get J omega times Z naught times C. That's the normalized admittance. And that's going to be equal to what? Right? Y'all with me? So that's J2. And that means C is equal to 2 over Z naught. And then it's going to be divided by omega. Can you tell me what that is? 2 over 50.
6.37 nanometers, or sorry, farads.
10 to the minus 9th or 10 to the minus 12?
Pico.
That's pico.
Oh, sorry.
Picofarads. All right. Y'all with me on this, guys? How many see this so far? You got it? With me on this? I'm just making sure. Yeah.
So how do we know that J2 is a capacitor, just because of how we found it?
Remember the one thing about this is an admittance, right? All right, I think impedance of a capacitor is negative J something, right? Admittance is positive J. All right, so I know that's going to be a capacitor. And then I go through, and I do it this way all the time. Well, what is capacitive reactance? It's 1 over J omega C. Then I normalize that, and then I take 1 over that because I need to normalize admittance. So I like doing it that way, methodically. And usually if you do it this way, you don't mess up. Because here's where the mess ups are. They'll have something like J omega C over Z naught. They'll think it's normalized. I'll divide it by Z naught. Y'all follow me on this one? They'll mess this up. People get confused because they'll normalize the admittance with an impedance, which is wrong. Okay? Yeah.
And you know it's in minutes because of the place that it was on the Smith chart.
I know that what I did was, I was in the impedance domain, right? I got to this point. Well, no matter what I do at this point, I don't have a real part of 1. See how the real part is 0.2? So I'm gonna add something that's an admittance. So to add an admittance, I come over here. Now, I'm on the rim, and the rim is exactly 1. Y'all follow me? That's gonna be, I call it the rim, it's the RQ1 circle. And I know whatever that admittance is, the normalized admittance here, I can find something that I can add in parallel to get rid of it. Okay, everyone? Now hear me on this one. What is the input impedance right there after I add that stuff?
50.
Just Z naught, right? In our case, 50 ohms. Y'all with me? That's the whole reason we're doing this, is so that we get rid of any problem of impedance matching. Now, in the past, you used stub tuning to do that, didn't you? You had either series or shunt stubs. And again, the reason you don't use stub tuning, a lot of times, with anything that's on these small boards, is they take a lot of surface space. And that's an important commodity. Surface space is the thing that is so important. You're gonna find out the biggest thing in a lot of these designs, especially stuff that's going into space on set, is size and weight. They want the smallest, lightest thing they can get up there and have it work. And there are more tricks than what I'm showing you here to do this, but these are good ones. These work. All right, now we're gonna do one, if you don't mind, outside of the rotated circle, outside of the Article 1 circle. And in that case, you can do it any way you want. And I'll show you the thought process. So here we go. I forgot which one this is. I think it's the last one I gave. Anybody do that one, by the way? How much time do we have? We got enough time.
7 minutes.
But I'll show you the thought process. And I bet you're starting to get it now. You know, I've not looked extensively on the internet, but I've not seen a good video about this on the internet. There may be, there probably are.
You will this afternoon.
You know, funny thing, see, in the past, all my stuff has been just for the class. I don't think I got anything. If you search for my name or this course and see if you get video, I don't think mine pops up.
I don't think it's tied to you. No, it's usually EMAG 2.
Because it exempts me of lawsuits. If the university, somebody wants to go after someone, good luck. I didn't do that. Thank God I have now. All right. Here comes another Smith chart. I hope you got one more. Okay. The last problem, what does it say for the last problem? Did you do it? Did anybody do the last problem I assigned?
I had it written down.
All right, what, can you tell me what it says, the specifics?
The load is 20 plus J50 and the line is 50 ohms.
This is an interesting problem. It's not the one I want, though. So ZL is equal to 50, did you say?
20 plus J50,
And what is Z naught?
50.
Okay, that means normalized is going to be what? 20 plus J50 over 50, right? Or it's 0.4 plus J1, right? Yeah, I guess this one will work. And take it back. All right, so I know this is J1 here. Right? And if I look at 0.4 plus J1, I'm going to say it's about here. Is that right?
Yeah.
0.4 plus J1. Let me just show you what I'm thinking. I think you'll see this. All right. Now, hear me now, so you'll understand the reason. It's real important. My end goal is to get right there by adding things, right? That's the goal of this, either in series or in shunt, and they have to be only reactive elements. Now look at this trajectory here. Y'all see here, if I add anything in series, I can get to this point and I can get to this point, right? Please just watch this. But if I add anything in series, I can't get to this point. This is something, the R equals 1 circle is inside that 0.4 circle. Do you all see that? So if I add in series, and just listen to me, I want to go through this and make sure you all see this. I can obviously add something in series. That's J.1. This is going to be something less than that, right? I don't even know what the value is, but it would be a negative J there. Do y'all follow me? So if I had a negative J, which would be a capacitor, I could land there. And then it's no brainer. If that's impedance, I go over here, that's admittance, then I go to the center. With me? I could keep going, and I would hit this point, right? With me? That was J. 0.1. I can keep adding J until I hit this point, which would have a negative J. Do y'all see that right there? This is a positive J value that's less than 1. It would be like J.4 or something, right?
Mm-hmm.
If I keep going, it's going to be at J minus 0.4, if that was. Y'all follow me? Now to get to minus 0.4, if I started at 1, I have to add a lot of negative. But I can still get here. Do y'all follow me? So in any case, if I'm going to do this, I would be adding a negative J impedance, right? Which is a capacitor. Y'all with me on that part? And hear me on the next thought. However, that's impedance, right? If I go right through here, I would have the load admittance, right? Y'all with me? The only thing I did is take 1 over this value and I'd be here. Y'all follow me on this? Right? Now that's still at the load, but now I'm looking at admittances that I'm going to add. And if I added admittance here, this is going to have a negative J. I could move, I don't even know what it's going to be, somewhere down here. I could move along the real trajectory of that, and I could add positive J, which would be an admittance, to get to this point. That would be in parallel. Do you all see that? Just realize what I'm thinking in my mind. I could keep adding and I could get up here to get the positive, some other positive point. Y'all with me? However, I can see that there are 2 ways to get to this rotated circle. One, by adding a series element. One, by adding a shunt element. Y'all see that? Series element is a normalized impedance. Shunt element is a normalized admittance. Either one works. Got me on this? Now, once I'm at this rotated circle, then 1 over that value puts me in the other domain. If it was impedance, I would be in admittance. But now I'm on the 1s. And that's where I long to be, because as soon as I'm there, I add an element to get rid of the reactive component, then I'm at the center. So that's why, if you're outside both of these rotated circles, you can add something in series or you can add it in shunt at first. It doesn't matter. And you can still get right here at the end. Now, I'm just about out of time here, but what else does he say in this problem? Because he probably put some constraints. There's 4 solutions to this, by the way, this particular one.
4 solutions.
It just says find all 4.
Oh, forget that. Let's find one, call it a day. Here, here's what I'm going to do. Right, just find this point right here for me. Just find that. Where 0.4 intersects the
Plus
road.
J, 0.5.
Yep.
All right, 0.4 plus J, 0.5 is this point, right? We'll call this point 1, this 0.2. That means in series, I add a minus J.5. Y'all see this, class? That was 1, I want to get it to 0.5, so I add a minus 0.5 J. With me? So here, we have the minus J 0.5. Then, take 1 over that, where are we then? I want to just show you the map.
It's about 0.1 minus J 1.2.
All right, not 0.
It's about 1.
1,
Oh, yeah, sorry.
1 minus J1,
Yeah.
1.22.
1.22. So that would be 0.3, right? That's an admittance, right? Y'all get that?
Yeah.
We need to add J 1.22 to get rid of that, right? This would be an admittance of J 1.22. I'm really out of time, but I think you see this clear enough. This is an impedance, right? Normalized? That impedance is a capacitor. So it would be what? Capacitive reactance is 1 over J omega C, right? Or minus J over omega C, right, guys? I normalize it, I divide by Z naught, and I set it equal to minus J.5. Down here, that's a plus J, but it's an admittance, right? All right, that's a capacitor too, because impedance of a capacitor is 1 over J omega C. Normalized impedance is 1 over J omega C Z naught. 1 over that is J omega C Z naught is equal to this. Got it, guys? Give it a shot. There's 4 possible solutions, but that's why when something's outside the rotated circle, you can add in series or in parallel. Yeah.
Can you give us any insight into the clue?
Yeah, it's on this. I mean, I'm fairly predictable. I think.